Swayam Prabha. Digital India. Educated India.
Okay, good morning. Today's topic is a vast topic, of course, as usual, and all of us know that structure determination is often taught in one semester, sometimes 2 semesters, sometimes for few years. It's such a vast subject, all of us know, because you studied in BSc, MSc, and then again we are going through it. But this is a kind of a special topic. Subject is a special, like heterocyclic chemistry. Similarly, the structure determination in heterocyclic chemistry also is tough. Why tough? I will give you some of the examples basically today, and also we will stress upon the use of carbon NMR and nitrogen NMR. Okay, these are the more useful techniques in heterocyclic chemistry. Okay. Why difficult, etc., all these things actually just basically will just give you some of these ideas. For example, a topic which could be from my research area, and it's a molecule, sit down, okay. This is a molecule which was, you see here, I am just drawing the structure. It's a pretty big structure though, pretty big structure with a big structure here, and then you have this quinone moiety, and then you have double bonds, then you have OAC, and here also one OAC. So, likewise methyl group, it is a beta methyl group, then free hydroxy, then a OH group. Okay. So, you see, then what? Then the nitrogen is substituted by a cyano group, which is called cyanamide, and the name of this molecule is kinamycin D, and which was isolated in 1970, and then the structure was established on the basis of NMR, IR, etc., all these things, including X-ray. Then in 1994, somebody like Stephen Gould from Oregon State, where I worked, he found that structure is wrong. Okay. What could be wrong? Actually, see, mind it, this was established by an X-ray examinations, X-ray crystallography, but eventually in 1994 he could show, sorry, here is a OH group of here, he could show that the real compound, what could be the real compound? CN should be NC, isocyanide. Okay. Basically, because the mass is compatible with this, sorry, in conformity with this structure. Okay, all other functional groups are in agreement. So, then what is the problem? That means, this particular compound defied the crystallographic determination, structure determination, right, and eventually it was found to be a molecule of this kind. It is a bench indinone kind of molecule, bench indinone. So, everything remains as it is, OAC and OAC here, then methyl group, then alpha hydroxy, alpha OAC, and what? And it is a diazo compound, which is quite unusual. In all of us know diazomethane pretty unstable, right? Diphenyl diazomethane unstable, but this is sufficiently stable to survive in natural products by microorganism, and it could be isolated, it could be chromatographed, you could do all kinds of things. So, what it means that this is just an example where the structure determination in heterocyclic chemistry could be too complicated. See, where you had all kinds of hydrogens and acetate etc., nothing was changed, but when it comes to the heterocyclic part, this molecule was changed. That means, X-ray was unable to map the NCN and CNN unit. Okay. Likewise, let us look at one more molecule. Here you have a pyrrole moiety, then it is an orthoquinone kind of moiety here, and then you have a pyridine nucleus and a carboxylic acid. This molecule is known as methoxetine. So, okay, if you look at forget this, look how many hydrogens are there altogether. There are only 5 hydrogens, right, and there is no aliphatic hydrogen. Sorry, 1, 2, 3, 4, 5, 6 hydrogen, but out of which many of you know that in NMR under normal routine experiments, we do not detect a carboxylic hydrogen unless we stop the exchange process. Then what else? Then you have all these aromatic hydrogens etc. Well, from the chemical shift you can make out somewhat, as you will see, you can make quickly. I will give you some examples how to distinguish pyrrole and pyridine by just by proton NMR. You can do it very quickly. Okay. That means, from there you can make out that there is a pyrrole unit, there is a pyridine unit, but how to ascertain the position of the nitrogen? It is tough. Okay. So, there are ways classically people used to do by degradation, means break the molecule into smaller pieces, then you write down the structure, determine the structure, then of course, then do the little back calculation to find out the structures for the such molecules. One thing which could be important is this carbon 13 NMR. What is the use of carbon 13 NMR? First of all, it is a high resolution NMR, it works for a wide range, all of us know. In addition, it is particularly useful for the carbonyl compounds, that you have to remember. Carbonyl compounds are nicely distinguished. Let us say you have an ester, you have an amide, you can quickly distinguish them. You have especially if you have a carbonyl group, ketone carbonyl or aldehyde carbonyl, they can be distinguished very easily from these other carbonyl groups. Okay. So, then often we will say that means in other words, for molecules which are proton poor means there are very few protons, then structure determination is tough. Then, but what are these typical methods? Typical methods, I think often we will see here in books. In books you will have UV, as usual IR, then NMR, NMR, then within NMR what are the nuclei often we deal with. There are plenty now. Okay, so about 40 different nuclei are regularly investigated to find out the structure, 40 different nuclei, maybe more, means including silicon, iron, cobalt, all these, okay, tin, indium, boron, all these. So, but commonly in heterocyclic chemistry we will be dealing with proton, carbon and fluorine. Okay, fine, I will take fluorine also. Fluorine also is an important nucleus. Phosphorus, okay, I will put it in the back side. 31 phosphorus, and I will put something more here, which is 15 nitrogen. It is a very important one, because most commonly we encounter nitrogen. So, these are the nuclei in heterocyclic chemistry are very useful. There is a group of compounds, phosphorus compounds. So, but if you go to the Silverstein's book, you know what you will find, there is no chapter on UV, there is no chapter on UV. Reason being they are not useful, but I will give you only 2 examples today, which are of recent examples, which are recent times. Okay. And even today that UV can be useful in heterocyclic chemistry. In normal carbocyclic chemistry etc., UV may not be useful, but in heterocyclic chemistry it is still very useful. I will just give you 2 examples. One is from my paper or rather our paper, and then one paper published in last year 2010. Okay, that how could UV be used. For example, we did a reaction, chemical reaction, and the molecule looks like this is a, and where you will have a cyclic aziridine. Sorry, aziridine is a cyclic, sorry, by tricyclic or pentacyclic or whatever you say. This was the molecule. Then we did a reaction called flash vacuum pyrolysis at high temperature, which is at 450 degree centigrade. I do not know whether you know or not the technique called flash vacuum pyrolysis. What is it? It is a high temperature, normally it is a high temperature reactions beyond 300 degree centigrade and vapor phase reaction. That means, you vaporize the solid and then allow to pass through a preheated oven under vacuum. That means, when you allow it to pass through the preheated oven, and the contact time with the heat is less, this is just for few seconds maybe. So, that means, the products if it is unstable after formation immediately drawn to the cold trap. So, I mean if you are we have a flash vacuum pyrolysis apparatus in our lab, homemade apparatus, you can do this, and then we got a compound here. Okay, got a compound here, and as usual when we took the NMR was too complicated, but one thing that was clear, that it was not an aliphatic compound. All the peaks were present in the aromatic region. So, in NMR aromatic region was identified. So, what is the product? This is the kind of first report how is new way of making a heterocyclic compound. Okay. One thing I can tell you, that flash vacuum pyrolysis exclude cyclopentadiene. That means, it is a reverse electrodiol reactions. So, one would expect that is so, that the product should have been this one, cyclopentinoaziridine. But unfortunately, the product was not this one, because it is an aliphatic, right. You will have aliphatic hydrogen, all these things. So, that means, alicyclic hydrogen I should say, they are all, but those were not present. So, what do you expect then? I will give you the structure, straight away without spending much time. The structure is what is 2-pyridone. It is a special kind of pericyclic reaction, pi 2a, pi 2a, pi 2s. Okay. So, but one can argue that now this compound also could be, compound also could be 2-hydroxypyridone. So, this was a problem actually, So, how to establish that? Oh sorry. So, how to establish this? That means, it is a problem of tautomeric mixture of compounds. how to establish which tautomers are present in a molecule. Let us say if you are handling with beta ketoesters, ethyl acetoacetate, you can quickly see it by proton NMR. Okay. You can, because in all form hydrogen is there, that comes at hydrogen bonded, because of the hydrogen bonding it appears at beyond a point beyond 10 or 12. So, you have a nice hydrogen bonded proton can be visible in proton NMR, that means keto tautomerism in simple cases could be easily been established. But in this case, how to do it? If you look at the NMR and if you see the NMR, you can actually propose both the structures, because this part is same, doublet all this etc. And this NH, that means basically you have to distinguish between NH hydrogen and OH hydrogen. How to do it? If you do the normally, if it is a labile hydrogen, all of us know we do D2 exchange, but that this will work actually for both the structures. So, then what is the other proposition? Okay, if you let us say a few minutes ago I said that carbon NMR is a very important one, that is what I thought in fact, but it did not work. Okay, for your information, this is our paper I published in 2009 and JOC. Okay. And I do not have the page number, but if you just go through the go to our name, this you will find this. Okay. So, but there is, you have to also keep it in mind, if you have an oxygen attached carbon, then that also has a very high chemical sheet value. For example, a chemical sheet value of this carbonyl of the pyridone should be around, any guess? 210. No, you have to be little careful. It's right, it's an amide. So, it's amide. Ester is around 170. Amide means always the first 2 digit is 16. Second, the third digit could be 9 or could be 1 or even less. So, it is less than 170 for sure. Okay. And for example, if you take let us say phenol, these are the things you have to be a little for example, if you take phenol here, what is the delta value of the carbon having the hydroxy? Any idea? If you are a practicing organic chemist, especially the research scholars, you have to keep it in mind. I mean, not exactly, roughly. For example, if benzene, what is the base value of benzene carbon NMR? No, carbon. No, roughly you have to remember 128. So, they add another 30. How much is 14? So, another 158. So, that means if you put an oxygen, there is a big increment of this. So, that is a very unique property of carbon 13 NMR. Okay. So, this is a very, that means if you want to identify oxygen containing aromatics, is easier to handle, easier to rather conclude with carbon 13 NMR. Okay. So, in case of pyridine, let us say 2-hydroxypyridine, what should be the estimated carbon 13 NMR? Carbon NMR having this carbon chemical shift of the this carbon having this OH group. So, it is a benzene 120, another is 150, then you have a nitrogen, electron withdrawing nitrogen. So, it could definitely could be greater than 150, that is for sure. So, this is around let us say 60. So, it is very difficult to distinguish. I do not exactly remember what are the values, but it is complex. So, eventually, but people suggested that if a molecule of this kind exists in the literature, there is a ratio of 9:1. That means 9 is the keto form and 1:1 is the enol form. But how to establish? Okay. The way it was established like this is a standard protocol available in the literature, and this was the major form, and the UV in this case was useful, and the UV was 230 nanometer. Okay. And the lambda max for the other compound, this one and this was 270 nanometer, 270 nanometer, fine. So, but we have not established the structure of the product of the reaction, okay, because it is a mixture. If it is a mixture, then actually you will have both 230 and 270. So, you have to have a pure compound, you have to have a pure compound. So, what we did, we reacted this mixture with silver oxide and methyl iodide, and eventually we locked this, right. Eventually we locked this, okay, and this experiment, they obviously this locking is this one, and it now you see this one is pretty close to this enol form, and this particular compound given NMR of this UV of 270, exactly 270. So, that means because substitution of hydrogen by a methyl group would not cause any UV difference. So, both the compounds, that means locked enol form was checked and it nicely matched, and so at least we could assume that the compound was in this form, but we cannot say which one is more, which one is less. At least one thing the conclusion was that this reaction gave the pyridone, but from this experiment we could make out only that the pyridone was formed, but still we could not establish whether it was. Then you go back to the UV etc., all these things again to establish or the NMR rather to find out. So, once you know that the pyridone is formed, then you can probably go through the NMR again and the solvent. There are many other techniques called solvochromatic studies. From there you can find out the ratio of the different enol forms, okay. And for in heterocyclic chemistry, this prototropic tautomerism is very important. Let me give you one more example. Let us say if you have pyridine, sulfur substituted pyridine, let us say. So, again all of us can guess the equilibrium would be, it is a thione equilibrium on this kind. That is pyridine 2 mercaptan, is in equilibrium, but which one is more, which one is less. In case of oxygen it was pyridone was the major 9:1, right, but in this case what should be the again is guess, again this thione is this one is the major one, but this is in equilibrium. Most of the reactions where the reacts 2 mercaptopyridine reacts, they go through this they undergo reactions through sulfur, right, and where do you use 2 mercaptopyridine? 2 mercaptopyridine, louder. Oh no, LPG, okay, right, okay, LPG, there is a sulfur compound, that's dimethyl sulfide, but it has to be volatile though, but 2 mercaptopyridine is not volatile, okay, but it is used as a reagent in a very important reaction called Barton, right, louder. Barton? No. Barton is famous for many things. Yes, Barton nitrosation reaction, all these things. Barton-McCormick deoxygenation. I may not exactly spell this McCormick, something like this. This spelling could be a little wrong, and it is called deoxygenation. What is it? It is nothing but, we have to also know these things. This is very important reactions. You just go through the Caruthers book, and this is there. It is a very famous reaction. If you have an oxygen up here, and then you have to some derivatization you have to do with this 2 markup to pyridine something I have forgotten at the moment okay. So, something then you have to do a radical reaction, I think there is a kind of radical reactions at the moment I have forgotten, maybe we have to see. Any case, so if you have sulfur and oxygen, the major tautomer is the keto form. And go to the next one, the other possible structure, let us say if you have 2 amino pyridine, in most cases this is then there are other possibilities, then other possibility is this corresponding imine form. One can I mean it is very difficult to distinguish them, but again from the UV studies you can make out that this is a purely aromatic, this is not a purely aromatic one, and for nitrogen it is the exclusive form, that is the amino form is the exclusive form. Okay. Amino form is exclusive form. Let us take one more example. This is a nucleus. I will be talking about say benzene, then a furanone structures with a compound, then other side you have again a furanone, but it looks like a lactone and hydrogen, and this is phenyl. Okay. Now, but normally whatever we know of, from there we cannot really write an equilibrium, right. We don't write an equilibrium, because ketone tautomerism requires is a ketone and an alpha hydrogen that is there. So, one can assume that there is a tautomerization toward these directions, right, but it has been eventually established again through UV study that the enolization actually breaks the aromaticity. Enolization breaks the aromaticity, and the compound that is formed, the enol that is formed is these ones. And so, this is actually the equilibrium lies here, and this particular compound enol form has been crystallized and examined by X-ray. Okay. And the structure is proven now. Structure is proven. Of course, it requires all kinds of studies, NMR, IR, UV, everything was studied, but this is a special feature. I mean, what is the driving force, that you have to see. That means, this is a published work, again this is published in 2010, JOC page number 690. Okay. So, X-ray favors this enol form, and then you have to support the X-ray also, because in the very first example I said X-ray is not the final answer, X-ray could be wrong, especially when you have tautomers and other things. Okay. But and it was also supported by UV, and this UV in this case. So, obviously, you have to first know what is the UV, and to do that what they did a reaction here, room temperature reactions. I will write this is TMS CHN2, and toluene is the solvent, and the temperature is room temperature. Okay. So, what do you guess? Diazomethane OCH TMS, right? Yes, that is what any case, but eventually actually the reaction that takes place, I will just write the only part structure here. This should be methyl. Eventually TMS goes out under the reaction conditions, okay, because it is so slightly acidic hydrogen, right. So, acidic hydrogen it comes out. So, it is just like a basically a high boiling substitute of diazomethane, and So, and what is it? It is again a locked enol locked enol or enol ether. And if you look at the UV of the starting one and this one, this has an UV 432 nanometer, 432 nanometer. So, it is so similar kinds of compounds of this enol forms they have been okay. But what is the driving force here? That is what you have to find out. What is the driving force to break the aromaticity of the starting compound? This is actually commercial, actually intermediate for a commercial dye, and I could not get the literature because it is patented. Okay. But it is a very useful and commercially available dye, but I cannot tell you the purpose for which they are made or they are commercialized. And what, so any guess why the enol form should be more stable or more predominant and rather than this aromaticity? Normally aromaticity is the driving force for most of the reactions, right? Dearomatization is not, but in this case is something different. It is if you draw the resonating structures of this molecule, what you will find, it could be if you draw this resonating structure here. So, you have a 5 member ring and oxygen and this is nitrogen. So, once again it is kind of a seed node structure, right. Polarized one, this the charge resides outside the skeleton. So, it should be a seed node kind of structure. So, and so can you make out, and that means it is in resonance with such a structure, and this such structure is not a stable one. Reason being, just like if you recall, I think in one of the recent seminars I raised this point that this molecule cyclopentadienone is a unstable molecule, is an unstable molecule. It is today, even today it is not isolable. It is not isolable. It is anti-aromaticity. So, this anti-aromaticity actually drives this molecule for the enolizations. But this example is to tell you that the UV is still required in certain cases, some especially ketoenol tautomerism and a case like this enol ketoenol forms. And so, let us look at maybe one more important area. One more important area, that is so UV we have talked about, and then all of us know this is mass spec. Mass spec is very useful. Mass spec is very useful. Okay. Then we will go to the NMR, because NMR we have all kinds of experiments. In mass spec, how to use mass spec in heterocyclic chemistry? All of us know nitrogen odd rule, right? What does it tell? This nitrogen rule in mass spec. If the molecular ion peak, mind it, if the molecular ion peak is odd, then the compound must have odd number of nitrogens, fine. But but that is not always true though. I mean, first of all, it is not true because of what? Because of the presence of even number of nitrogen, that is one thing. Secondly, you have to note that molecular ion peak may not be visible. That is an important thing, may not be visible, it could be misleading, and thirdly, it could be these even odd number of nitrogen compound may be accompanied by halides. Like I have an example here, this was published in 1995, it is an alkaloid. What you will see, if you do this chemical analysis etc., you will get the molecular ion peak, molecular formula etc. It is a tetracyclic molecule, and you have a plus charge here, then this methoxy and methoxy, all these. So, basically okay, and molecular formula is found out to be from analysis, our mass spec is found out to be C21O4 nitrogen and C. So, what do you see here, just you have a single nitrogen, but if you record the Fab mass, right, FAB Fab mass these days no longer used. Fab mass is not very popular after the invent of ESI spec, ESI mass. ESI mass, you have to know this terminology. Right, FAB is fast atom bombardment mass spectrometry. People, this is not popular now. It has lost its popularity. Now, the most common one is what we have now, ESI, electron spray ionizations. Okay. So, this mass spec actually mass spectral data gave a value 348, that is the highest peak, and this was 100%. So, obviously, one would jump to the conclusion that this peak is due to the molecular ion peak, and it is an even number. So, even that means it must have even number of nitrogen, but what you see here, eventual conclusion that the compound is not. Okay. And so, that means you have to be little cautious. This is just an example. I have many more, rather I have quite a few information here, but I do not want to give you those information, but this is just an example that although the molecule has an odd number of nitrogen, but the which one? Oh no, this is methyl group, this one. Oh yes, it is actually this is the natural products. It is a natural products. It is a natural product, and it has a hydrochloride salt. Okay. What else? And what the other? I mean, mass spec of course it gives you the exact precise molecular formula. So if you have a high resolution mass, and the quickest also, and if you do not have a high resolution mass, you can also make use of it, especially for the detection of the sulfur compounds. How to detect sulfur compound? Let us say you are given a molecule, and you have to find out whether the molecule contains sulfur. How do you do? It could be aromatic, it could be non-aromatic, it does not matter. How do you do? So, sodium fission test? No, we do that of yes, many times it is very useful, but most often these days I think probably from now on, from in another few years, I think nobody will do that, those sort of tests, right. Okay. I mean theoretically one can do it by ESCA, electron scaling microscopy, right, for chemical analysis, electron microscopy for chemical analysis, ESCA, then XPS, X-ray photoelectron spectroscopy, XPS. So, all kinds of spectroscopies are there, which will basically find out the ionization potential or rather ionization or binding energy for ejection of the electrons. But other than that, but for us or for organic chemist, actually the best useful is the, I mean, if you can like to know that mass is very important. If you have a record here, mass here, let us say this is M, this is a peak for let us say M plus molecular ion peak. What is then immediately after, what you see here, M plus 1, of course, then the next what you see, M plus 2. But in case of sulfur, if you are just careful, in case of sulfur, what you will find, M, then M plus 1, and then M plus 2 is little longer. That just basically they are all minute thing, but this gives you a nice indication. Why? 34. No, but this abundance, natural abundance. In case of nitrogen, let us say 14, 15. What is the abundance of nitrogen? 15. How much? This is also very important in NMR spectroscopy. What is the natural abundance of nitrogen? 15, something like 0.4%. 0.4%, that means 99.6% is basically nitrogen 14, okay, and 0.4% is this one. And then case of sulfur, it is the sulfur, then that is 34 sulfur is 4.4%, 4.4%. Okay. So, it is significantly high. So, from there you can actually make out whether the sulfur is present or not. And we used to do a small calculation, from there also we could make, I mean, that is actually the old version of Silverstein would give you some small calculation to find out that how many carbons are there, how many hydrogens are there, how many nitrogens are there. But these days if you have high resolution mass, straight away you get the molecular formula done. So, that is not a problem at all, but so that means from there also you can make out, but unless if you do not have, then of course you have to go to something else. And then rest is basically next thing is be proton NMR. Proton NMR, how do you distinguish? Okay, let us say I will give you a basically I will give you a problem, that means in NMR. So, you have proton and then 15 NMR and of course, the carbon NMR, right, carbon NMR. So, these are the three things often do. Then we have plenty of experiments, and then you have to have also the parameters. What are the parameters we deal with? Chemical shift, what else? Coupling constant, integration, that is all. And anything else? Yes. Other experiments would require NOE, that is COG, that means correlation spectroscopy. These are these, and correlation spectroscopy could be of many kinds, okay. Correlation spectroscopy, and so if you, that means just NMR is too complex. Actually, again in NMR there are maybe 15 different 50 different experiments are there, maybe more, not less, and all kinds of programs, all kinds of NMR programs are there to evaluate coupling constant, to evaluate chemical shifts, all these things. But some of them are reliable, some of them are not. But these days again people have been trying to calculate chemical shift by using a standard technique called DFT. What is DFT? So, all of us know now. So, okay, and let us say how do you quickly basically you have to do little quick test here in the case of the aromatic chemistry or aromatic heterocyclic chemistry. Suppose we are expecting a compound could be pyridine, or it could be a derivative of, let us say, pyrrole. How do I do? How do I evaluate without going through the chem draw other things mentally? In NMR, reference compound is very important. Reference compound is very important. Just just one or two values for reference compound, then you can extrapolate the chemical shift. For example, all of us know, right, for benzene, what is the chemical shift value? Delta, right. Then we what should be the chemical shift value of the pyridine? You have 3 different kinds of the protons. Grossly, if you do not remember any value, grossly, let us say you are handling a pyridine, you have taken the NMR. How do you quickly come to the conclusion that that is the NMR of the NMR of pyridine? Now, which one you look for basically? Let us say I am expecting or suspecting this molecule is pyridine, now we check the NMR. Now, we have to conclude that this is pyridine or not pyridine. How do I know? Okay. In case of, let us say, in case of chemical shift should be higher, because in whole system you have benzene. Now, carbon has been substituted by a more electronegative atom. So, then overall somewhere at some point one of these hydrogen should be downfield shifted, that is all. So, in fact, and in this case you can see the this one is 7.55 and this one is pretty close to pyridine, though sorry benzene, it is 7.1, but this one the one that is alpha to the nitrogen, it is 8.52, 8.52. So, that means you do not have to remember the values, you just look for a signal which will be appearing at a higher delta value. Okay. Similarly, if you are suspecting let us say pyrrole, so what should be the pyrrole, what should be the value? Just a guess. Again you have put the electronegative atom. So, I mean you can always expect a little higher delta value because you have, but at the same time we are now heterocyclic chemist. We know that lone pair of electron is delocalized and it is shared by all the carbon atoms, and that means at least one, that means 2 electron divided by 5 atoms. So, 2 by 5th electron densities are around. So, that means electron density has increased. So, the chemical should right upfield, that is all. That means what is the reference point? Benzene. So, it should be on the right hand side of benzene, and benzene, and in this case what I will find again, this is 6.2 this hydrogen, and this hydrogen is 6.6. Okay. So, basically just your reference point either benzene or chloroform. If you see something on the right hand side, it is likely to be this azole compound, 5 membered heterocyclose compound. Okay. And there are plenty of I mean in a book, but there are very few books though which will give you, but recently we have purchased one book called Handbook of Heterocyclic Chemistry. There you will get find all these details data, but roughly you have to have this idea. And let us say now if you let us say you go for carbon, let us say this is for the proton. Similarly, for you go for the carbon here, what is the best value for benzene? 128 few minutes ago I said, fine. Now, let us say if you are suspecting a pyridine derivative, what do you expect? Pyridine derivative at downfield. Okay, let us see how much is it. Let us say the remotest one, in the remotest carbon from nitrogen, this is 136, and this one is 124. This meta one is, you see here meta one is little I mean it gives you polarized structure, because of that it is less. And then as you can see here, the one that is attached to nitrogen 150. You remember a few minutes ago I said you have oxygen is at plus 30. So, so roughly so that means, so this is pretty diagnostic that this carbon has a chemical shift line. Okay. So, I mean you can just draw the resemblance from your compound of this kind, for example. What should be the chemical shift value of this carbon? You know now the base value 128. So, you have a nitrogen now attached to it and the electron withdrawing group. So, again 150, well in this case it is close 148. Okay. So, now we are heterocyclic chemist again, heterocyclic chemistry. So, let us take another molecule. I think all of us know this molecule, right? What is it called? It is pyridine N-oxide. Pyridine N-oxide. You take pyridine, just hydrogen peroxide, acetic acid. Acetic acid, it will straight away give this compound. It is nice compound, crystalline compound. Okay, and its reactivity is different. Reactivity is different. We all know the resonance, right? Because of the resonance of these oxygen electron pairs, and what you will find, the pyridine ring is now electron rich compared to the parent pyridine. That means if the electron density increases around the ring, obvious conclusion would be that the electron density would be increased, means chemical shift decrease, and that is what we will see for this hydrogen, this carbon here now it is 139. So, you can just extrapolate all these things without much problem. Okay. And so, let me that means basically the trend in electron density or the chemical shift is important here. There are examples also will give you where you can go for the coupling constant. Yes.
Meta carbon pyridine has upwind shift and benzene.
Right, right. You just draw the structure eventually. Basically, I mean, it's very difficult to at the moment say. You have to just draw the structure and see which one has higher weightage and which one non is higher weightage. Okay. It's a polarized one, not like benzene. It is like homogeneously delocalized. In case of heterocyclic chemistry, it is not a likely. I mean, all the carbons will have electron density, same electron density, because of the polarized structures. Let me give you. This is a very important one. J value. J value is very important in again in heterocyclic to distinguish heterocyclic nucleus from non heterocyclic nuclei. Okay. How do I know? There is a guideline. There is a guideline. J values. I think this is a standard formula. J value decrease. J value decrease with, I think, with increased electron density. With increased electronegativity. And when I say J value, that means 3J values decrease with increased electron density. Okay. What does it mean? What does it mean? It means that if you have a coupling, let us say this is all of us know, right? These two hydrogen 1, 2, 3. So, the coupling between these is known as 3J. What is the standard value for aliphatic compounds? Aliphatic compound, you have to remember, the organic chemist you have to remember, coupling constant 7 Hz. Let us say when I say ethyl ester, ethyl ester means you have a quartet and a triplet, but the coupling constant, if it is an aliphatic one, it has to be around 7. Okay. Now, just what you do, you just change this carbon into an heteroatom and put hydrogen. So, what is the coupling constant? Then now the coupling constant should be between 3 to 4 Hz. That is what I meant to say, that if you incorporate an electronegative atom into the skeleton of a 3J coupling, then the coupling constant decreases. It is a very diagnostic, because many of you know that we often deal with furan compounds. In our lab, when I do the furan compounds, so our reference again, let us say this hydrogen and this hydrogen, and our reference is here 3J in benzene. What is the coupling constant for benzene ortho hydrogens? 7 to 8. Okay, standard value is I think 8. Standard value is 8. So, now you see what should be the coupling constant between these two hydrogens in furan. Guess, you have an electronegative atom, by the way, and they, of course, the angle etc. also have changed, and but this value is, I will give you this value is 1.8, very small. So, that means you are having an aromatic proton, and then you see a coupling constant, very small coupling constant, almost always is likely to be a heterocyclic compound. For example, let us take another example like pyrrole. In this case of pyrrole, this hydrogen and this hydrogen would couple to each other with a constant 2.6. Okay. In case of thiophene, you can see electronegativity decreases, right, in this order: furan, pyrrole and thiophene. Now, so what do you expect? It should be a little more, right, and in this case it is 4%. I mean, to give you one more example, probably this is quite interesting. Suppose you are expecting a disubstituted pyridine, let us say, or just a monosubstituted pyridine, for example. Okay. So, there are two possible structures. Let us say this is a possible structure, and then another structure could be this structure. Okay, how do you distinguish? It is very difficult. It is very difficult, but okay, let me give you one more structure. I think how is that? I think this is better option. This one, let us say. Let us say, forget about this one. Let us say between these two, this, let us say this dimethylpyridine, this dimethylpyridine. How do you distinguish them? There are two, yes, splitting pattern, of course, that is the number one. Number two, chemical shift also useful. You have two downfield protons here, in this case one. Thirdly, you can just use the coupling constant values. This coupling constant, this one, these two hydrogen, indicated hydrogen would be more than these two coupling constant. That means this is what 2 3 hydrogen and 3 4 hydrogen. 2 3 hydrogen has a coupling constant, this has a coupling constant 4 to 5.7, and if you go to the 3 4, the coupling constant goes to 7 to 9. What does it mean? Because these hydrogens are closer to the nitrogen, that is all. If the hydrogens are closer to the electronegative atoms, the coupling constant is likely to be less. So, this is a very important diagnostic. Okay. And so, I think let me just quickly go to the one more example, then we tomorrow we will talk about this nitrogen 15, for example. This is a paper from 2012. It is a fresh paper actually, and this is CC means chemical communication, and the page number 277. It is a very interesting compound. Only just in last month they have found a different structure. For example, there is a structure. The name of the compound is I forgot, I guess nitrone, something like that, some nitrone, not nitro, okay, nitrone, and the structure was originally proposed to be a triazole, means nitrogen and nitrogen here, hydrogen, and this, mind it, and this was the structure and proposed, and people believe that this is the structure and this structure, okay. But only recently a group of scientists has proposed, no, this structure is wrong, this structure is this. There is a nitrogen up here, triazole, triazole. So, nitrogen should be also here and also here. Okay. So, that means on your left, what do you see? This was the old structure, old one, and this is the new one. Difference, the old one is proposed to be a Sidnone structure or mesoionic compound, charge lying outside this. There is no proper resonating structure. Okay. And in this case also, the right hand side also, this is new one, this is not a resonating structure. And why is it? What is it? By now all of us know, right? Okay, who will take up this topic for research scholars? Anybody is it interested? Okay, if you know NHC, if anybody is interested in reviewing NHC, because all the research scholars have to write a term paper, right? Write a term paper, and so you pick up this topic NHC, N heterocyclic carbene, nitrogen heterocyclic carbene. Okay. What do you see? The carbene is stable now. This molecule is commercialized. But it is stable. And who is the discoverer of stable carbene? Officer, do you remember? Arduengo. Good. Which year? 1991. Good. and this is another carving 2012. You see a stable carving, you can bottle it, you can sell it, okay, it is a nice one. But how to establish the structure? I mean, what did they do? Basically, they did a reaction with sulfur, just sulfur, THF and room temperature. Sulfur, THF at room temperature. What is the expected product? Expected product is nitrogen, carbon and nitrogen. Okay, fine. And this molecule here is this. So, what do you see? Carbon NMR. Again, an example of carbon NMR. This carbon appeared at 229. So, that means carbon NMR again is useful for the heterocyclic compounds. Okay. And so, next time we will have little more on this nitrogen heterocycle. Okay. Now, on nitrogen heterocycles and nitrogen NMR rather.